We are the University of Waterloo Steel Bridge Design Team. We're a group of passionate students that use our classroom and workplace knowledge to solve unique engineering problems. We're proud to present our 2026 bridge design, and we'll be going over the design, analysis, fabrication, and construction process in this video.
Welcome to the Petit Kodiak River in Moncton. Moncton is a rich cultural center known for prominent attractions like Magnetic Hill. Only two bridges exist across the Petit Kodiak at Moncton, the Brenda Robertson and Gunningsville bridges. To better connect communities across the river, a new steel bridge is being proposed. Incorporating recycled steel material, the proposed bridge will support pedestrians, cyclists, and mobility vehicles from above while also clearing the river below, avoiding disturbances to recreational activities, the river ecosystem, and the Bay of Fundy's famous tidal bore.
This site presents a unique set of constraints. First, with the footing placements requiring a cantilever section on the east end and a protected navigation channel in the middle of the river requiring additional clearance. Furthermore, construction is limited to the grounds east of the river.
This year's bridge is a 215-pound brown truss with 47 members. It features a tied arch on the west end and a cantilevered east end. To design this bridge, we modeled this year's loads and constraints in Altair OptiStruct to create a material density heat map optimized to reduce structural costs. This heat map was used as a basis for several possible geometric configurations. Thousands of manual iterations were performed across these configurations in order to optimize their cross-sections and determine their lowest possible costs. We ultimately chose a brown arch design for our solution. Finally, we validated the specifics of our design using a Python script connected to SAP 2000's Open API, allowing for a more thorough optimization of the cross-section.
We used SAP 2000 as well as Excel spreadsheets we developed to extract the lateral and vertical deflection, to estimate our costs and verify capacities of critical sections. Moreover, after repeatedly load testing last year's bridge and referencing prior year's numbers, we determined that we would apply an adjustment factor of 3 to our simulated aggregate deflections we obtained from SAP to translate software results to real-world results.
Our fabrication team was tasked with modeling the bridge in SolidWorks. The university's engineering machine shop then ensured that our drawings were realistic and manufacturable. Recycled steel was ordered locally from metal supermarkets in Kitchener, processed with CNC machining and water jet cutting, and finally welded into the main 47 members.
This year, we focused on reducing idle time for our builders and increasing flexibility in our team compositions by designing each site in a way so that they could be built by one builder at a time, minimizing our impact to the river system. While the bridge was being fabricated, we decided on a construction procedure using Navisworks, predicting the construction time of different sequences and combinations of builders. We ultimately decided on one barge and one land builder.
Our construction procedure this year features several novelties. The south stringer is assembled upside down while balanced on top of the east footing in the riverbank to reduce travel time for the barge. While being assembled, the truss can slide back and forth so that the barge can remain stationary. The builder on land puts together assemblies and delivers them to the riverbank, assisting with holding the truss when needed. Once the south stringer is built, it is flipped over and connected to the footings. The north stringer is assembled on top of the south stringer before being lifted into place and installed by the barge. Finally, the lateral members and arches are installed, completing construction.
The bridge uses a combination of improved connection designs from previous bridges, such as Waterloo's tongue and groove connection, along with new and unique connections that can be quickly installed onto the truss by one person. These connections were standardized as much as possible throughout the bridge and were designed to avoid alignment difficulties. For over 12 years, our students have honed their skills, bridge after bridge, year after year. We at the University of Waterloo Steel Bridge Design Team hope that we can continue to provide sustainable solutions for communities across Canada.
We'd like to take this time to thank our sponsors for their continued support throughout the years. Our achievements wouldn't be possible without their continued help.